Now coming to the spontaneity of a process, we will see the relationship between enthalpy change and spontaneity. Now the spontaneous process is very important in thermodynamics. It's very important. We should know that what are the factors which are responsible for the spontaneity of a particular process. Now we also know that every system, it tries to attain what you can say the minimum energy. That is, the energy should always be in the lowest position. Alright, every system tries to attain the lowest energy, the lower energy, we can say that. And how it is being possible? That is when the value of delta H is negative, means when the heat is released, means when the reaction is exothermic. I have told you many times, when the reaction is exothermic, heat is released, so less energy is present in the given compound, we can say that. Clear? So now when delta H is negative, it should favor the spontaneity of a particular process. So basically exothermic reactions have a tendency to proceed what you can say spontaneously. Exothermic reactions. For example, suppose we can say that like that is a substance upon heating. Alright, when you are heating a particular substance, I have told it in my last video also. When you start the heating of a particular substance, initially you start. After that the reaction is spontaneous. So the heating is continued. The heating, that is when you are heating a particular substance, energy is released. So less energy is present in the compound and hence the compound becomes stable in nature, we can say that. When evaporation is taking place, but here a question comes. Evaporation, what you find is that it is not an exothermic reaction. Evaporation is an endothermic reaction, but it is a spontaneous reaction. Just now I said you that every spontaneous process takes place by the lowering of energy, when the energy is released. That means what you find is that all exothermic reactions are spontaneous. That means I mean to say that spontaneous reactions are exothermic in nature. We can say that. Always the spontaneous reactions are exothermic in nature, but there are also certain reactions. Listen carefully. There are also certain reactions which are also endothermic and they are also spontaneous. For example, evaporation of water. It's an endothermic process. It's not an exothermic process. Alright, it's an endothermic process. It's not an exothermic, but it is spontaneous in nature. When NaOH is added to HCl, it gives NaCl in water. It is nothing but what you find is that it is released there. It's an exothermic process. Alright, when ammonium chloride is dissolved in water, listen carefully. When potassium nitrate is dissolved in water, it is not released, it is absorbed. It's an endothermic process and it is also spontaneous in nature. So that means I should say that del H negative is not the only criteria for the spontaneity of a process. Del H negative, because I said you initially that every spontaneous reaction takes place with a lowering of energy. Means energy is released. Alright, but we come to see several examples as I said you, that is where the reaction is endothermic, but the reaction is also at the same time spontaneous in nature. So hence I can say that del H negative is not the only criteria for the spontaneity of reaction, because I started from an enthalpy change and spontaneity. So I said in that if the enthalpy change is negative, then it is spontaneous. But again and again I am repeating that this is not the only criteria for the spontaneity of a reaction. That means there must be some other criteria also. Got it? There must be some other criteria also for the spontaneity of a reaction, because not only all exothermic reactions are spontaneous. At the same time, many endothermic reactions are also, you can say, it is spontaneous in nature. We can say that. Got it? So many of the endothermic reactions like evaporation of water, dissolution of ammonium chloride, thermal decomposition of sodium carbonate, etc. are all spontaneous in nature. They are all endothermic reactions and they are all spontaneous in nature, so to say. So in reversible reactions, if the forward reaction is exothermic, remember that the backward reaction will be endothermic. So reactions which have got a negative value and of delta H and the positive value of delta H go hand in hand. Got it? In a reversible reaction, if in the forward direction is exothermic, then remember that in the backward direction is endothermic. So negative value in the forward direction, negative value of delta H, and in the backward direction there is a positive value of delta H. They go hand in hand always. Got it? They go always hand in hand. So as I said, the del H negative is not the only criteria for spontaneity of a reaction. Then there is also another criteria for the spontaneity of reaction. What is that? Randomness. Alright, randomness. Now you must be wondering, what is randomness here? Okay, let me give an example to you. I am giving you a tray. Alright, a tray I am giving you. And I am giving in that particular tray 10 white balls and 10 black balls kept separately. 10 white balls and 10 black balls are kept separately, a big tray of course. I am giving you and I am asking that you hold this particular tray. This balls, as you can see, it is kept separately. You move from one end to the other end of the room but without disturbing the balls. Will it be easy for you? No, it will be difficult. Why? Because as you hold the tray and you move from one place to another, there are every chances, 99.9% chance is there that the ball is going to intermix with one another. What is that called? That is called as randomness. Alright. So when they intermix with one another, that is what the reaction is. When the ball they intermix with one another, what the reaction is? It is a spontaneous reaction, because I said you 99.9% chances there or 99% chances there that the ball will intermix with one another. It's a spontaneous process. Alright. So when the spontaneous reaction is taking place, there is an increase in randomness, because when the ball is being kept separately. Alright, it is not randomness, it is in the orderliness. But when there is a randomness, there is a disorderliness in the system. Because when the ball will mix with one another, there is a disorderliness in the system. So, when the randomness increases, disorderliness increases. Alright. So, all spontaneous reactions, listen carefully, all spontaneous reactions are accompanied by increase in the randomness of a particular system, is accompanied by the increase in the disorderliness of a particular system. Let me give another example to you. For example, I have taken two, cylinders having two different gases present in it. Two different gases. Let us say in one cylinder I am having nitrogen gas, in another cylinder I am having helium gas. Alright, it is being kept in two different cylinders. Now what I am doing is that I am interconnecting by the help of a pipe, the two cylinders. I am interconnecting it. Now there are two valves present in it. Alright, so that when I open the valve, then the gases will mix with one another. Alright. Now when the gas is present in the two different cylinders, nitrogen gas and helium gas, kept separately in two different cylinders, it is in what? Orderliness or disorderliness? Orderliness. It is kept in two different cylinders. But when I am joining with the help of a pipe, when I am interconnecting with the help of a pipe and I am opening the valve, then what happens? The gas, they intermix with one another. Nitrogen gas comes from here, helium gas comes from here. Then what happens? They intermix. So what happens? Randomness increases or decreases? Increases. So this particular reaction is a spontaneous reaction or a non-spontaneous reaction? It's a spontaneous reaction. Again, the same thing. So every spontaneous reactions is accompanied by increase in the randomness of a particular system. Alright? It is increased in the disorderliness of a particular system. So we got another factors for the spontaneity of a particular process. So del H negative, as I said, it's not the only criteria. There is another factor is also there. What is that? Randomness or disorderliness. Now the question is, how will you measure randomness? Before measuring the randomness, we will come to some of the factors which affect the randomness. The first is your physical state. You can write down the factors affecting randomness. Atoms and molecules of a solid are tightly bonded to, and they are in the least randomness. Or in case of solid, because they are tightly held. So hardly the molecules or atoms they are able to move. So they are in the orderliness, they are not in disorderliness. Alright, so hence randomness increases when they change from solid state to gaseous state. Randomness increases, disorderliness increases when it changes from solid state to gaseous state. So remember that. That is when randomness increases in this way, solid when it changes to liquid, got it? And when it changes to gas. So randomness increases in this way. Got it? Randomness increases in this manner when it changes from solid to gas. We can say that. Clear? Because the gas molecules are far apart from each other and they strike with one another. Alright, when they are far apart from one another. So there is a disorderliness, there is a randomness. But in case of solid, the molecules are tightly held, closely packed. So randomness is the least, we can say. Rather, there is an orderliness. Fine. So physical state is one of the factors. Next, temperature. On increasing the temperature, the kinetic energy of the kinetic energy of the molecules increases. Due to which the randomness or disorderliness increases. We can say that. Clear? Pressure. Gases at low pressure are having greater randomness than at high pressure. When at low pressure, suppose a gas cylinder is there, less amount of gas is present. The gases can easily move. So randomness is more. But in case of high pressure, what happens? The gases are not, they cannot move easily. Alright, you must be knowing it. When the gases are high pressure present in a cylinder, in our home, it is said to be as what? LPG, liquefied petroleum gas. It may change into liquid also. Alright, and I've said it, in case of liquid, the randomness is less. In case of gas, the randomness is more. You can see it here. Now, next is complexity. A large molecule have greater randomness than any other subatomic molecule or submolecule, or when the fragments existing in the same phase, we can say that. Alright. So, when it's more complex, a large molecule has greater randomness because it is more complex in nature. The molecules strike with one another. Alright. Then the fragments, small, we can say that, molecules of the same matter, we can say. Now, dissolution of a substance in another substance. What it increases its randomness. Like when ammonia gas is dissolved in HCl, we can say. Alright, it is passed through HCl, then it forms what? Ammonium chloride. Clear? So, there from gaseous state to solid state it happens. Randomness is decreasing. The sublimation is an example of, solidification is an example of a decrease in randomness. But sublimation is an example of increase in randomness, because in case of sublimation, the substance changes from solid state to gaseous state. So there is an increase in randomness. But in case of solidification, it changes from gaseous state to solid state. There is a decrease in randomness. Alright, fine. Next is chemical decomposition. Whenever there is a decomposition reaction is taking place, for example, mercuric oxide and heating, we give you mercury and oxygen. There is an increase in randomness because there is a breaking up of bond. The molecules collide with one another. So hence there is an increase in randomness. Whenever there is an intermixing of particular substance, there is increase in randomness. For example, we have taken some water and we have put some salt into it. There is an increase in randomness because in between the water molecules, sugar molecules will come and take its place. So the molecules is going to collide with one another. There is an increase in randomness. We can say that. Conversion of solid into liquid. There is an increase in randomness. Because solid to liquid, increase in randomness. Fusion, melting, there is an increase in randomness. Liquid to solid, solidification, decrease in randomness. Alright, so in this way, what you find is that there are several factors which helps in increasing the randomness of a system. So the driving force which is required for the randomness of a system is that the tendency to attain its minimum energy, we can say, and tendency to attain a state of maximum randomness. That's a driving force, we can say that. For overall process, we learned it that to attain minimum energy, first of all, the reaction is taking place, and second is to increase the randomness to attain the maximum randomness of a particular system. So based upon this, we come to a factor which is called as entropy. Alright, based upon this means, how will you measure this randomness? How will you measure this disorderliness? We can measure it by a factor which is called as entropy, denoted by the letter capital S, we can say that, which is known as entropy of a particular system. Alright, so what is entropy? Entropy is a property of a substance which measures the disorderliness or the randomness of a system. It's a particular factor which measures the randomness or the disorderliness of a particular system, we can say that. How to measure the randomness? It's quite an absurd term, no? That is randomness, how to measure it. So we measure it by the help of what you can say randomness or disorderliness of a system. We measure it by the factor which is called as entropy, we can say that. Now entropy is a state function, just like enthalpy and internal energy, it is a state function, we can say that. So it depends upon the initial and final state of the system. So we can also calculate the change in entropy. So delta S is equal to S final minus S initial, we can say that. S final minus S initial, that is known as a change in entropy. We can calculate the final state minus initial state when the reaction is given to you. That is product minus reactant. That also can be said. Final means product, initial means reactant. So product minus reactant, that will also give the entropy of particular system. Now if a system undergoes change from initial to final state, then it's this. Now suppose if a chemical process, for any chemical process, we can use this particular formula. For any chemical process, we can say that. but for a reversible process. Alright, for a reversible change, we can say that. How will you calculate delta S? Delta S is equal to Q reversible by T. This is the formula to calculate the change in entropy. That is Q reversible by T when the process is at equilibrium. So hence the unit of entropy is Q is measured in joules and T is measured in Kelvin. So joules per Kelvin, we can say that. Alright, or calories per Kelvin, we can say that. Clear? In this way, this is the unit of entropy, we can say that. Joules per Kelvin or calories per Kelvin or calories per Kelvin per mole also, we can say that. Clear? So in this way, when a reaction is it's reversible, when the reaction is a reversible process, then Q reversible by T. Now why is Q reversible by T? Because Q reversible is the amount of heat supplied at a temperature T in a particular process, in a particular reversible process. Now why do we say it's for a reversible process only? Because it is too difficult to define the actual entropy for a particular system. It is not so easy because I said, randomness is quite an absurd term. Alright, it's quite an abstract term. It's an abstract term, we can say that. Quite difficult to define, that is randomness. Alright, so it is difficult to define the actual entropy. Means we cannot measure the absolute entropy particular system. Absolute entropy. Because absolute entropy means entropy of the system plus entropy of the surroundings. That is called as the entropy of the universe. And it is not easy to determine the entropy of the surroundings. Alright, because as it is not easy to determine the entropy of the system, then it is quite difficult to determine the entropy of the surroundings. Because what is surroundings, I said? Surroundings is that part of the universe which is not in our study, which is not concerned in our study. That is called as surroundings. So it is very difficult to measure the entropy of the surroundings. So hence it is absolutely impossible to measure the absolute entropy of a particular system. Absolute means total entropy of a particular system, because total entropy is entropy of the system plus entropy of the surroundings. And as I said it is not easy to measure the entropy of the surroundings. But I don't say it is impossible. I'm not using that word. It can be done. You will see later on. I will say. Alright, but for the timing now, I am saying you that it's not possible to measure the entropy of the surroundings. We can say that. Then what will do? For that particular reason. However, in the study of thermodynamics, we are mainly concerned with the change in entropy, and is denoted by delta S, as I said, which is given by the Q reversible by T. And Q is the heat supplied to a temperature, and the positive sign of delta S indicates that increase in randomness. When delta S is positive, delta S can have three values, either greater than 0, less than 0, equal to 0. If delta S is greater than 0, then the reaction is spontaneous. You can say that. It's positive value. And randomness is increasing. If the delta S is negative, then the reaction is non-spontaneous. Randomness is decreasing. And if the delta S is equal to 0, the reaction is in equilibrium. You need to remember this particular, we can say that. This particular thing, you need to remember it. So in this way, based upon this, we come to see that if you take the entropy of the solid and entropy of the liquid and entropy of the gas, already I have said you that is entropy of the gas is always more than that of the liquid, is always more than that of the solid. Alright, now the next question you may ask here, why is Q reversible by T? Why it is only not Q by T? Alright, why it is Q reversible by T? Because for a reversible process, the change in entropy, for reversible process, the change in entropy is 0, we can say that. Whereas for an irreversible process, that is the isolated process, the entropy change is greater than 0. Alright, now next is, as I said, for reversible isolated process. Now this is not an isolated process, mind it. This is simply a reversible process. When it is reversible isolated, means a single process is given. Alright, but reversible process is generally taking place in number of steps, infinite number of steps. Alright, so if a reversible isolated process, isolated single, we can say that, it's given, then the change in entropy, that is delta S, is equal to 0. But for an irreversible process, we can say that the change in entropy is greater than 0. Remember it is an isolated, I am saying you. Fine. Now my question remains the same only, that why we take it as Q reversible by T? Why not Q irreversible by T? Or why not only Q by T? Because, now listen carefully. For a reversible process only, the heat can be measured, because reversible process is a slow process. It is taking place in infinite number of small steps. But irreversible process is very fast. Practically, can you calculate the heat in an irreversible process? For example, that is conversion. We can say that. Something is burning. Can you calculate the heat? It is quite difficult. Why? Because an irreversible process is always taking place in one particular direction and is very fast. Very, very fast it is. Got it? The time interval is infinitesimally small. So practically it is not possible to calculate the heat in an irreversible process. But as reversible process is a so slow process, as it is taking place by infinite number of small steps, for that reason practically we can calculate the heat. So hence it is written Q reversible by T. I hope you understood. Hence it is written Q reversible by T. Because here if I write Q irreversible process, then it is not possible basically. Theoretically it can be. I can write the formula. Why not? I can write theoretically, I can write Q irreversible by T. But practically you think of irreversible process is a very fast process, and it is practically it's not possible to calculate the heat in an irreversible process. So hence we use the term that is reversible process, so to say. Alright, hence we use the term that is reversible process. And for a reversible process only, we can know which is the initial and which is the final state. But for a reversible process, we can know which is the initial and which is the final state. But for an irreversible process, it's very difficult to know when the reaction has started and when the reaction has stopped. It's quite difficult to know. So hence for that particular purpose, we take the heat, we calculate the heat for a reversible process, and we put the value here and we calculate the value of delta S, so to say. Now in this way, it's entropy change in an ideal gas. How to calculate entropy change in an ideal gas? Now when I say ideal gas, then it's ideal isothermal reversible process of an ideal gas, so to say. Alright, that is isothermal, not isolated. Alright, isothermal. So when I say isothermal, that means delta U is equal to 0. Delta U is equal to 0. What I said, delta S I am going to calculate for ideal isothermal reversible process of an ideal gas. See the condition, remember the condition is very important here. So for an isothermal process, delta U is equal to 0. Del S is equal to Q reversible by T. Already I have said you, it is reversible isothermal process of an ideal gas. Fine. Now next is del U is equal to 0. So del U is equal to Q plus W. Isn't it? Now W is equal to nothing but minus Q, or we can say Q is equal to minus W. Now what is W? W is equal to minus 2.303 nRT log V2 by V1, isn't it? For an reversible isothermal process of an ideal gas, we have studied this particular one. W is equal to this. Now when I will calculate delta S is what is that? Q by T, isn't it? Q by T, and Q is what? Minus W. So minus of minus, it will be what? Plus 2.303 nR. Now T by T, T and T also will cancel. So log V2 by V1. Alright. So Q is equal to minus W. See here. And W is this. So when I put the value of Q here, minus of minus, it will become what? Plus. So plus 2.303 nRT log V2 by V1 by divided by T. By T. So TT will get cancelled. So this. Or we can say in terms of pressure 2.303 nR log P1 by P2. That also can be said. So this is the value of delta S for a reversible process. We can say that reversible isothermal process of an ideal gas. Now if Cp and Cv is given, alright, then delta S is equal to 2.303 Cp log T2 by T1. You can write it down. Delta S is equal to 2.303 Cp log T2 by T1. And delta S is equal to 2.303 Cv log T2 by T1. Again it is. Alright. So when the first one was isobaric process, because I said is Cp. Alright, heat calculated constant pressure. And the second one was isochoric process, because Cv, heat calculated constant volume. Alright. So in both the case, delta S is equal to, again I repeat, 2.303 Cp log T2 by T1 for isobaric process, and for isochoric process, delta S is equal to 2.303 Cv log T2 by T1. Okay. Thank you.